Hello and welcome to OpenLogic. In this video, we're going to look at the concept and the application of a UVM factory. First, let's try to understand the problem before UVM came along. And this is a class, it contains only one byte. And this is a test bench where we instantiate the class several times and we call randomize for each of them. We can think of this class as a stimulus, and this is a test bench where it drives the stimulus into a design. Let's say we have a new requirement where the byte must be an even number. What are the solutions that we can do? Well, first we can add the constraint directly into the class. And this is okay if this requirement was previously missing and we are now correcting its behavior. But if this is an additional requirement, then inserting this constraint is a very bad move, because by doing so, its original intent is lost. To add extra requirement on top of existing one way is by using class inheritance. In this example, class D extends class C. It has the byte and a new constraint which makes sure the byte is always an even number. By doing so, class C is not contaminated. Now, how do we use class D? One simple way is by replacing the instance class here with D. But doing so is the same as the previous example where we lost the original intent of class C. One other solution is by having both C and D in the same test bench. We can use an if statement to select whether to instantiate the C instance or the D instance. However, this is not a scalable solution. In this example, we have 3 C instances and we need to replicate this code for all of them. And this is troublesome, especially if these 3 instances are located at different files. And then there's a possibility where there is another requirement where we need another extension, and then we need to expand this code to cover for that new extension. Now, is it possible that we introduce this new requirement and be able to reuse all this existing code without modifying them? At this point, you may be thinking, nah, you must be talking crazy, there's no way we can reuse all this code. Well, thankfully, this can be done, and let's see how UVM achieve it. First, a constant reminder, whenever we are trying to use UVM code, we must import the UVM package. And second, all classes should generally be extending from a UVM class. For example, class C here can be extending from UVM object, and if we are using UVM object, we should be using UVM object utils and a constructor like this. The same modification should be followed by class D. And finally, the constructor call here, it should be replaced by a somewhat longer UVM version. Alright, let's rearrange the class to understand what we have changed. And this is a UVM utils macro. We use this in every class so that they are all registered into a factory. The factory then has the capability to replace class instantiation. Besides the factory registration, this macro also introduces additional functionality into the class. One of them is this create function, which is used to replace this new constructor. The new constructor always returns an object based on the instant class type. For example, C0 belongs to class C. The create function, on the other hand, allows for type override. C0 can be instantiated as an object of class D. Now let's see how we can achieve that. Now there are many ways to achieve this type override. One of the ways is by using this set type override, which is introduced by this UVM utils macro. Basically, by calling this function, we are saying that we want the class C to be overridden by class D. At this point of time, you may ask, if we are adding this line into this file, then we are not exactly reusing this file, right? And yes, you would be right, but there are many ways to overcome this. For example, we can write a brand new module and insert this code there. In this way, we would not be touching this original file. However, there's a catch. We need to make sure that this line here is executed first before these 3 lines here. If we are only using initial blocks, then it wouldn't work because there's no way to tell which initial block will run first. Now, if we want to avoid all these troubles, there's a way introduced by UVM, which is by using a simulation argument, UVM set type override. By using this simulation argument, we can change the type of these instances without having to change this class and this test bench. All we need to do is to introduce this new class and then use this simulation argument to override the type. There is, however, one requirement. The new type must be extending from the original type. And this is a very powerful feature of UVM, where it allows us to reuse code as much as possible and at the same time allows us to change the behavior of existing test bench. Well, except that this code doesn't work. There is no compilation error, the simulation will run, but the type override will not happen. These instances will still be instantiated as a class C object. Do you know why? First, I recommend going through the UVM Hello World video. Once you go through that, then you understand this is not the best way to learn UVM. In this example, there is a simulation argument. This argument needs to be processed by a code, and that code has not been executed in this example. So even though this is a legitimate simulation argument, it would not be taking effect. The better way to learn and run experiment on UVM code would be by using UVM test. This is a UVM test called myTest, and as with every UVM based class, it has a UVM util macros and a constructor. The UVM test also has a task called run where we can put our code there to execute. For example, we can declare C0, instantiate it, and randomize it. Note that I have omitted C1 and C2 compared to the original code because I'm out of space. This is a simple test bench module where we import UVM package and call run test. These are the three contents that follow the original requirement. If we run this simulation using this command, then the run test will pick up this simulation argument and instantiate myTest. And then it will call run and instantiate C0 as a class C object, and it will randomize it where the byte B will be randomized to any number. The class D here is based on a new requirement. If we run the simulation using this command where there is a set type override from class C to class D, the run test will do the same thing where it instantiates myTest and call run. But at this point where C0 is being instantiated, it will check if there has been an override, and since there is one override, it will try to instantiate a class D object instead. And when we randomize C0, the constraint would take effect and therefore B will always be randomized to an even number. Note that we have now changed the behavior of these three contents without modifying them. What we have done is adding this new piece of code and set an override from the command line. Once again, with this capability, it allows us to reuse the existing code as much as possible and at the same time allows us to add modifications to change its behavior. Alright, now we have learned two ways of overriding a class type, one through the command line and another through the code. If you are using UVM test or any other UVM component, there are two other functions. The first one is set type override by type, and the second one is set type override. This one requires the argument of the class type where you can get by calling getType of a particular class. This one takes in two string variables and you have to put the class name in string. Generally, I wouldn't recommend this one because it's a longer. This one is shorter, but I would still recommend this one because this one is usable by anyone. These two are only usable when you are inside the UVM component. Besides these functions, there are also others which allows for finer control. For example, there's a setInst override. SetInst override is the same as setType override, and it allows you to specify which instance you want to override. If we have C0, C1 and C2 here, then this command will only override C0. And similarly, this function has many variations whether in code or in simulation arguments. I'll skip them for now. You may find these variations easily online. Now, before we go, I just want to point out one thing. This is a video about UVM Factory, and if you have paid attention, we actually have not seen UVM Factory. Well, in UVM, many classes and implementations are abstracted away from users, and UVM Factory is one of them. All these UVM utils macros, this create function, and these override functions, they are all related to UVM Factory. For example, calling this setType override function will eventually be calling UVM Factory to implement it. If you are interested, you can actually use the UVM Factory functions directly. First, understand that UVM Factory is a singleton class, which means in the whole simulation with UVM, there can only be one UVM Factory instance. So we need to get the handle to that factory by using a static function get. Once we get that factory handle, we can use its function. For example, set type override by type. Calling this factory function is the same as calling this function. As a matter of fact, using this function we will eventually call the factory version. But as you can see, using the factory version is somewhat troublesome, so we recommend to use the wrapper function instead. For most cases, there would be wrapper functions available, and you may never have to encounter UVM factory at all. But in my opinion, it is good to know what is UVM factory and how it is being used. Well, that's it for this time. Thanks for watching. I hope you find the video helpful. Do help supporting by clicking like, share and subscribe.